Good evening, everyone. My name is Aditya Sharma, and this is Fundamentals of Compressible Flow course being conducted by Department of Mechanical Engineering, IIT Guwahati, under the NPTEL program, National Program on Technology Enhanced Learning. And this is the eighth week of this particular course. And we have been discussing expansion waves and oblique shocks. Okay. And the focus of this week's discussion has been on the reflection and interaction of expansion waves and oblique shocks. Okay. So, interaction of oblique shocks and oblique shocks. Interaction of one oblique shock with another, and then how oblique shocks and expansion waves interact and all this. So this has been covered in this week's content. Instructor for the course is Professor Niranjan Sahu from Department of Mechanical Engineering, IIT Guwahati, and I'm a research scholar here and teaching assistant for these tutorial sessions. So we shall start this session in another couple of minutes to see if somebody joins. After that, we'll start the session. Okay, so we can start with today's session. Okay, so expansion waves and oblique shocks, reflection and interaction. So these are the lectures that have been covered in this week's content, lecture number 18 and lecture number 19. So lecture number 18 deals with uh, shock polar. So major topic here is one is shock polar and then pressure deflection diagram. Okay. And then in lecture 19, we have intersection of oblique shocks. Okay. Intersection of oblique shock and Mach wave, Mach reflection, wave reflection from a free boundary. So these topics are there. Okay. So we will first see topics of one lecture and then questions related to that lecture, and the same way for the second lecture. Okay. So theta beta m curve first topic is there. Okay, then shock polar is there. Then pressure deflection diagram is there, and then regular reflections of oblique shocks. So this is there. Right. Then first is theta beta m curve. Okay. So this is week 8, fundamentals of compressible flow. Then we have what is the date today? It is 17. Then lecture number 18 is there. So theta beta m curve. First is theta beta m curve. So theta beta m curve we'll see from previous lectures content only. So this is your theta beta m curve. Okay. So on your y-axis you have your beta. Just- Yes. So first topic is your theta beta m curve, right? So on your y-axis you have beta and on your x-axis you have theta, right? And this kind of curve you get. Okay. And if you see this diagram, you can see that for a single deflection angle, you have two solutions of beta. One corresponds to the weak oblique shock and one corresponds to the strong oblique shock, right? Okay. Then next is your shock polar. Okay. Now what is shock polar? So shock polar basically gives you uh, velocities. Okay. And which velocities? So that is downstream of your shock, oblique shock. Okay. That is at the back of your oblique shock. Okay. In front is your flow stream conditions, right? And then at the back, uh, how the shock has affected this your flow or the Mach or the velocity. So this basically is there. So two diagrams have been shown. First is this, okay, this. So this is there. Now what are these diagrams? So if at the back, okay, so it is like this. So you have flow here, okay, and then there's some theta deflection is there. Then you have a shock here forming, okay, which deflects your flow this way. Now this was M1, this was M2, okay, or V1 if you multiply it with the speed of sound, okay, M2 or V2. Now this V2 has been given here, okay, and we call this plane as photograph plane, right? This we call as photograph plane. Now this is for one deflection angle. Let's say this was theta. But for all deflection angles possible, so locus of all those points, okay, that give this velocity behind the oblique shock. So that basically is shock polar. Now, how does this shock polar looks? So it looks something like this. Okay, it looks something like this. So this is Vy. This is Vx. Okay. Now let's say we take some point here. Okay. Now from your origin, if you draw this line, okay, so this angle will be the deflection angle, and then these components will give the velocities in x and y direction, right? Now from this diagram, we can get the wave angle also. And how so? So what we will do from this end, okay, I'll call it A. From this end, I'll draw a line that will pass through B, okay. And from origin, I'll draw a perpendicular to this line, okay. Now this line, now this line, OH line, the angle that is making this OH line with the x-axis. So this gives your shock wave angle, right? Then another thing is there, which is your sonic circle. So what is with sonic circle? So all the velocities, okay, that uh, or all the oblique shock solutions. So if you see this OB line, right? So this cuts the shock polar at 2 points, right? So I can call it B and B dash 2 points. So there are again two solutions of this oblique shock at this theta. So we have seen in this theta beta m curve also that for single theta we have two solutions. Same thing again pops up here that for one theta we have two solutions. Then which one is weaker and which one is stronger? So the one which comes within the sonic line, right? So B dash. So this B dash corresponds to your strong oblique shock, and your B corresponds to your weak oblique shock. So this is there. Okay. Then how your shock polar behaves with Mach number. Okay. So the behavior of your shock polar with Mach number looks like this. So this is your shock polar for yes. Okay. So your Mach is increasing in this direction. Let's say this is M1, this is M2, and this is M3. So your M3 is greater than M2 is greater than M1. So the effect of your Mach number on shock polar. So this is there. Then analytical equation of shock polar also has been given to us. Okay. I believe that you can see from your uh, lecture videos only. So I'll give the link to this lecture number 18 in the description. Then what do we have? So this we discuss. Next we have pressure deflection diagram. So this pressure deflection diagram basically is your, this gives information about your static pressure behind the oblique shock wave along with your uh, deflection angle. Okay. So static pressure and theta. So pressure versus theta, this is the diagram. Okay. So how does it look like? So let's see that. something like this. Okay, perfectly symmetrical. Maybe you're not able to draw, but okay. It looks something like this. Now, this x-axis gives your theta, y-axis gives your pressure. That is static pressure. And what we have learned about static pressure, what happens to static pressure across the oblique shock. So behind your or downstream of your oblique shock, your static pressure increases. Okay. Now with theta, what happens to this static pressure? So this point, first of all, corresponds to your pressure ahead of uh, shock, oblique shock. Okay. Then there are two lobes. Okay. So this lobe is for your left running wave, and this is for your right running wave. Okay. Now, what is left running wave and what is right running wave? So left running wave basically is, so if your wave is like this, this is your theta and this is your wave. So this is basically is your left uh, running wave. Okay. And here, if you see, now if your this is your theta and this is your wave, right? This is your wave, oblique shock wave. This is your oblique shock wave. So this basically is your right running wave, and this is your left running wave. Okay. So positive theta values for your left running wave and negative theta values for your right running wave. Now this one location is for your pressure ahead of shock wave. Then if you change the deflection angle, then you'll have this as your static pressure at this theta angle, right? And this is your Q max, okay? The maximum deflection angle, and at this, you'll have this pressure. So this is it about your pressure deflection diagram. Then you have regular reflections of shock wave, oblique shock. Okay, next topic is regular reflection of oblique shock. Now, what happens in your regular reflection of oblique shock? So two walls are there. Okay. So you have some flow happening here, right? Then some deflection you give here. Okay. Then this deflection will give rise to an oblique shock. Okay. And this oblique shock will get reflected this way. Okay. And the flow that is happening, so it will be like this. Right. This direction and then this direction. This is theta, this is theta. And this is your beta 2. And this one is your beta 1. This is your reflected shock. This is your incident shock. Okay, so this is your region 1, this is your region 2, and this is your region 3. So first observation here is that your reflected shock wave is weaker than your incident shock wave. So shock wave, this shock wave will be weaker than your incident shock wave. First observation is this. Okay, because your deflection angles are same, but your MAC has reduced, right? Because M1 will be greater than M2, right? And then for this reason only your uh, shock wave angle, reflected shock wave angle will be, so your beta 2 will be less than your beta 1. Okay. So this is about your regular reflections of oblique shock. Then let's see the questions. So first question is there. Please read this question and try to answer this question. So this says that the shock polar is a graphical representation of oblique shock properties for all possible shock wave angles at different Mach numbers. So this is for a single Mach number, right? This is related to deflection angle, okay? And that too, the velocities. So in that case, this is false statement. So this basically is about shock polar. So if you know shock polar, so that should suffice. Okay. Then next question is, as the deflection angle is increased, the x velocity component of the, so what happens? Please try to answer this question. As the deflection angle is increased, what happens to the x velocity component? So this can be answered using your shock polar. Okay. So you see your shock polar. Okay. So this is one deflection angle. This is second deflection angle. Then this is third deflection angle. So let's call it theta 1. Okay. Let's call it theta 2. Let's call it theta 3. And theta 3 is greater than theta 2 is greater than theta 1. Okay. Now see their velocity components. X-axis. What is happening to their velocity components in x-axis? You see for theta 1, Vx1 is higher, Vx2 is lower, Vx3 is the smallest. Okay. So this is for Vx1, Vx2, Vx3. So as you increase the deflection angle, your x component of the velocity that decreases. Okay. So second question will be the correct answer to this question. So this is there. Then next question we have. So this is from definition of shock polar. So the locus of all the possible velocities ahead of shock can be plotted as shock polar at that Mach number. So this is behind and not head. So in that case, this is a false statement, right? Then next question is there. For a weak oblique shock at zero deflection angle, gamma is and gamma equals to 1.67. Find the characteristic Mach number value when the upstream Mach number is infinity. So this we have to find out. Four options have been given to us. So how can we do this? When your upstream Mach is infinity, so your characteristic Mach number m star is to be found, and the formula for this is gamma plus 1 over gamma minus 1 root. So this is there. So then question number 4, m star becomes this. Now gamma we have as 1.67 plus 1 minus 1. So this we have. So this is 2.67 divided by 0.67 root. So let's calculate this. So this comes out to be 1.9962, which is our answer. And if we look at the options that are given to us, So option B is the nearest option to what we have calculated. So moving on to next question in that case. So this is our next question. So please read this question. And try to answer this. So the question asks about your sonic circle. So inside the sonic circle in a shock polar, all the velocity components have dash values and represent dash shock solution. Dash oblique shock solution. So see your shock polar, and then this is your, basically this is your sonic circle. Inside the sonic circle, you have strong solutions, and outside of it, you have weak solutions. Okay. Then inside, you have strong solutions. Okay. So B and D options are there. But then if you have a strong solution, then your velocities will be subsonic. Okay. So in that case, the correct answer comes out to be B. So this is their question number 5. Then next question, question number 6. So shock polar has been given to us, and the question says that for a specific Mach value, the farthest point lying on the abscissa of a shock polar represents a dash. So for a specific Mach value, the farthest point lying on the abscissa of shock polar represents a dash. So farthest point on abscissa, this is your abscissa, this is your ordinate, basically x-axis, y-axis. So farthest point is point A. So in the previous question, we were talking about one of the previous questions, we were talking about sonic circle, and the solutions within the sonic circle are strong solutions of oblique shock, and outside are the weak solutions, right? And the weakest solution in your oblique shock is your Mach wave. And the farthest point is A. So this corresponds to your Mach line. Okay. So option number A. So this is the correct answer to your question. So E point is your strongest solution, that is normal shock. And this farthest point is your Mach wave. So this is question number 6. Then moving on to question number 7. A reflected oblique shock is weaker than incident shock in regular reflections. In regular oblique shock reflections. So this was your deflection of theta. and this gave your flow this deflection, and then here it started moving again in the same direction in which it was there in region 1. Okay, now M2 is less than M1 because across your oblique shock, your Mach decreases, right? Now, but deflection has remained the same, right? So, because Mach has decreased, so the reflected oblique shock becomes weaker than the incident shock. So, this is true statement. Okay. So, this was it about lecture number 18. Then we have lecture number 19. So, in lecture number 19, we have intersections of oblique shock. So, we are left with 5 minutes for 1 hour to complete. So we can start with lecture number 19. After that, we'll take a short break of 5 to 10 minutes. So intersection of oblique shocks. So first we have oblique shock of different family. So lecture number 19 is there, which talks about oblique intersection of oblique shocks. No, opposite. So opposite family. So one is your left running wave and one is your right running wave, right? So it will be like this. So your oblique shocks will intersect like this. And then from here, your slip line will arise. So it will be like this. This is your A oblique shock. This is your B oblique shock. So it will first move in this direction. And then this will move in this direction along the slip line, parallel to the slip line. And this will go like this, and this will again be parallel to your slip line. And what is your slip line? Why do we have a slip line? Because there are entropy differences across the slip line. Okay. Though the pressures are same, static pressures though are same, but there are entropy differences are there. So this is your region 1. This is your region 2. Okay, this is your region 3. This is your region 4. And this is your region 4 dash. Okay, so this is there. Now in this region and this region, the static pressures are same. Okay, but then your entropies are not same in these two regions. That's why we have a slip line. So this is your opposite family. Okay. Then for your same family, so same family means there will be oblique shocks that will be either left running or either right running, right? So this was left running, this was right running. So intersection of oblique shocks of same family. So this is like this. This is one theta. This is another theta. It is like this. Then this is your reflected wave. So this is your first oblique shock, this is your second oblique shock, and this is your reflected wave. So here your flow will go like this. Okay. Here you will have a slip line. Now talking about the regions and the pressures, static pressures and your so this is your slip line. So talking about the first, your flow will move from oblique shock A, then oblique shock B, right? And then from reflected wave, it will move. So this is one case. One case is that your flow will move from 1 to directly region 5. So it will not have to pass through two oblique shocks and then a reflection, this reflected wave, right? So what is the difference between these two cases is that though the pressures, static pressure between at 4 and 5, okay, will be same, but then the entropies are not going to be same between these uh, in these two regions. Okay, in region 4 and in region 5. So that is why we have a slip line here. We get a slip line here. So this is there. Then oblique shocks and Mach wave. So this has also been discussed in your lectures. So maybe you can refer to your lectures for this. Okay. Then Mach reflection has been discussed. So Mach reflection basically is so when you're so you have flow moving in this direction. Okay. You have this, let's say, deflection, and this is giving rise to an oblique shock. Now what happens is that now for this flow that will happen in region 2, the deflection that this wall is serving is greater than theta max. Okay. Is greater than theta max for this case here. So in that case, we know what happens, right? So we are going to get a normal shock here. Okay. Now it starts as normal shock, but away from your wall, away from wall, it interacts with your oblique shock. This is your oblique shock. Oblique shock and gives rise to this curved shock. Okay. So this basically is your Mach reflection. So this is there. This is your normal shock. Then last topic is wave reflection from a free body. So what happens here? So 2 points are to be noted here. Okay. So this you see, one example is jets. Okay. So the jet that gets ejected in atmosphere, right? So there you see that at the end, if you have an oblique shock, so this oblique shock is going to interact with your free boundary, okay? Because there are no strict boundaries in your atmosphere when you are ejecting your gas into atmosphere or jet. So two inferences are there. One is your oblique shock gets reflected as an expansion wave, okay? And then your expansion wave gets reflected as an oblique shock. So these two inferences are there. So these are the topics that have been discussed in your lecture number 19. Then we shall see questions now. So question number 8. So before starting question number 8, we can take a short break of 5 minutes. Then we can take the questions. Thank you. Okay, so we can start with the continue with the remaining session. So this is there. So two oblique shocks of opposite family uh, fill in the blank after interaction. So they refract after interaction. Okay. So question number 8. So opposite family, this is there. Opposite family. And then question number 9 is there. In case of intersection of two oblique shocks of opposite family across a slip line, the velocities are not in same direction. So that is false because velocities are there in same direction. Even their pressures, static pressures are same. Okay. So this you can see here. So this and this. So this becomes a false statement. Then question number 10 is there, which says that in case of intersection of two oblique shocks of opposite family, across the slip line, the static pressures are different. So static pressures are same. Okay, in case of intersection of two of opposite family. So this again this diagram here P4 is equal to P4 dash. Okay, so this is there. So Static ratios are different. This is false statement because P4 is equal to P4 dash. Then question number. So in case of intersection of two oblique shocks of opposite family, there will always be a slip line. So whether this is true or false. So this again is false. Why so? Because if your these two angles, deflection angles, if theta1 is equal to theta2, in that case, you will not have a slip line because entropy changes are going to be same for your refracted oblique shocks. For your refracted oblique shocks after intersection. So this is a false statement. So this again is a false statement. So your oblique shock gets reflected as an expansion wave. Okay, and expansion wave gets reflected as an oblique shock. So from a free boundary, an oblique shock reflects as an oblique shock. This is false statement. This as an expansion wave. Okay, question number 12. Then question number 13 to 16. So this is there. 13 to 16, we have to do questions, numerical questions, and for that, this information has been given to us. So for this, we need one question number 13 to 16. We need one formula. This so this formula we need at some point. Now what is given to us? From there we will start this numerical. The diagram has been given first of all. Okay. So your diagram is like this. You have first deflection, and then you have this. Then you have second deflection, and then you have shock wave related to this. Then you have shock wave related to this. So this is theta 1. Okay. So first, your flow moves in this direction. Then it moves in this direction. Then it moves in this direction. This is theta 2. Then this angle becomes theta 1 plus theta 2. Okay, and this angle becomes your beta 2. This becomes your beta 1. Here, shock wave angles. M1, region 1, region 2, region 3. Now let's see what the question has given to us. So M1 is given to us as 2.5. P1 is given to as 1 atmosphere. T1 is given to us as 290 Kelvin. Theta 1 is 12 degrees. Theta 2 is 6 degrees. Okay, this is there. So for Mach 2.5 and this. So first question, what it says. So in the tables we have theta beta m, theta beta m. Okay, theta beta m relation data. Then normal shock properties we have. Calculate the Mach number at region 2. So we have learned that only the normal component in oblique shocks, only the normal component has effect of the oblique shock. Okay. And the component which is along the shock wave, sorry. So it has no effect, correct? So what we will do, so one, this we will be using, and one this we will be using. Okay, from the this velocity triangles. So this is there. Also one more is there, which is m2 is equal to mn2 by sine beta minus theta. So these we are going to use. Okay. Then here we need to calculate question number 13 solution. M2 we need to calculate, right? So for M2 we need Mn2 sine beta minus theta. Now theta here is theta 1. Okay. So beta 1. Now theta 1 we have, Mn2 we don't have, beta 1 we don't have. So beta 1 we can get from the data that has been given to us. So for M1 equals to 2.5. So first table, if you see, theta 1 is equal to 12 degrees. Your beta 1 will be equal to 35.8 degrees, right? And then your Mn2. So your Mn2 square will be equal to, let's see what is, so gamma we are going to take as 1.4 only. Yeah. So for 1.4, Mn1 square. Now what is Mn1? So maybe first I'll just write down yes. So this is there. Now Mn1 is, if you see here, wait, Mn1 is M1 sine beta. Okay. M1 sine beta is equal to 2.5 sine of 35.8 degrees. So if you calculate this, this will come out to be 1.46. Okay. Please confirm the calculation. If there is some mistake, please write down in the comment box. Then mn2 square is equal to 1.46 square plus 2 by 1.4 minus 1, 2 into 1.4 divided by 1.4 minus 1 into 1.46 square, then minus 1. So this is there. Now if you calculate this, mn2 square is going to be 0.5122, implies mn2 is going to be 0.7157. Okay. Now from here, now m2 is equal to mn2 by sine beta minus theta, implies m2 is equal to 0.7157 sine 35.8 minus 12 degrees. So m2 will come out to be 1.7736. So this is your m2 or 1.77. Now m2 we have, okay, so 1.77. Now we want to calculate MAC at region 3. So this is region 3. Now for region 3, MAC is 1.77. So for MAC 1.77, so it should have been 1.77 here. So there is a mistake here. So this was right, but this was 18 degrees. Okay. So in that case, your beta 2 becomes 60 degrees. Right. Now we can calculate this mn2 dash. So this mn2 dash is analogous to this mn1. Okay. So mn2 dash is analogous to mn1 here. Okay. So, and m1 is analogous to m2 dash is analogous to m1, right? And then in case of beta 1, we have beta 2 here. So then mn2 dash here becomes 1.77 because MAC we have. So for your second oblique shock, you have incident MAC is 1.77 and sine of then 60 degrees. So this becomes 1.5328. So this is there, right? And in similar way, now across the this oblique shock, second oblique shock, okay, this second oblique shock. So now for this, we will use mn3 square is equal to mn square plus 2 by gamma minus 1 divided by 2 gamma by gamma minus 1 mn2 dash square minus 1. So this is there. Now mn3 square is equal to 1.53 square plus 2 by 1.4 minus 1 divided by 2 into 1.4, 1.4 minus 1. mn2 dash square is 1.53 square, okay, minus 1. Now if you calculate this will come out to be 0.4771. So if there is some calculation mistake, please let me know. So mn3 becomes 0.6907. Now in that case, mn3 is, sorry, m3 is mn3 divided by sine of beta 2 minus theta theta, yes, maybe you can call it the aggregate as theta 3. So this, so implies m3 is equal to mn3 is 0.6907 divided by sine of 60 minus 18, I believe. So 18, and this then becomes 0.6907 divided by sine of 42 degrees. Now if you calculate this, your m3 will come out to be 1.0322. Okay. So this is there. M3 you have calculated. So this was question number 03. So 1.03 is your MAC here. Now it says that calculate the static pressure at region 3. So we need to calculate the static pressure at region 3. Yes, so we need to calculate the static pressure at region number 3, right? So P2 by P1 will be calculated based on your this normal component. Okay, Mn1, which is 1.46. So for 1.46, your P2 by P1 is 2.1, right? So question number 15 solution. So we need to find out P3, right? So first will be calculate based on Mn1. Okay, P2 by P1 is equal to 2.1. Okay, from your table implies into P1. Now your P1 is 1 atmosphere. So this becomes 1 atmosphere, right? Then based on Mn2 dash, your P3 by P2 becomes 2.6. Okay, implies your P3 is 2.6 into P2. Now P2 is 2.1. So this becomes 5.46 atmosphere, right? So this is question number 15. Then next is calculate the static temperature at region 3. Now, same method we will use. Question number 16 solution. T2 by T1 is 1.2. Okay. Based on this Mn1 implies T2 is 1.2 into 290. So this becomes 348 Kelvin. Then T3 by T2 is 2.6 based on Mn2 dash. Okay. Implies your T3 becomes 2.6 into 348. So this becomes 904.8 Kelvin. So this was your last question of this session. Okay. So this is it about today's session. So I'll conclude this session. There were two lectures in this week's content, lecture number 18 and 19. So lecture number 18 was on shock polar, then pressure deflection diagram. Okay, so shock polar was about your velocities behind the oblique shock, है ना? With respect to your deflection angle. Then your pressure deflection diagram is about your static pressure, which changes with your deflection angle. Then there were left running and right running oblique shocks. Okay. Then we learned about regular reflection of oblique shocks in lecture number 18. In lecture number 19, we saw intersection of oblique shocks. So intersection of oblique shocks of same family and then intersection of oblique shocks of different families. Same family when two oblique shocks of either right running oblique shocks or left running oblique shocks, if they are intersecting, then it means they're of same family. And if a left running oblique shock is interacting with the right running oblique shock, then we say it's of opposite family. Okay, so these are the major things about lecture number 19. And then we studied how the oblique shocks when interact with a free boundary and expansion waves when interact with a free boundary. So what happens? So all this we discussed in lecture number 19, and in at the end we saw one numerical based on our regular reflection of oblique shocks, right? So this is it about today's session based on week number 8 of fundamentals of compressible flow. So next session again will be on coming Tuesday with same timing 6 to 8 p.m. Till then, goodbye. Thank you. Thanks for watching this session.